Yeah. And he put a potential, he put a charge on that flow of particles and so forth, and used a magnet and demonstrated the charge of the electrons. But I just want to show you that electrons are in everyday use. All this is a battery source, as you all see there. And there's a flow of electrons that are running through the copper coil. And anytime there's a flow of electrons associated with it is a magnet force perpendicular to it. But we can tap into that and create a motor. So there's nothing magical here, no Harry Potter stuff going on here. But basically the electrons are flowing through the copper wire, being attracted because of the magnetic component associated with the particle of the electrons moving, being attracted to the magnet, that's that little yellow disc. And the result is momentum carries that yellow disc over. So essentially you created a motor. That's how a motor works. Now we can also reverse it and play with the, manually move that coil, take the battery out, and we create a generator, we create electricity. So we can manipulate the magnetic property of the electrons flowing, or we can manipulate the flow of the electrons to create a motor or a generator. But those electrons are, for being so tiny, do a lot of stuff. Right, so let me take that off because that could be kind of distracting. Give me 1 second here. There we go, that's a little bit better. All right. And so the question was asked about dot structures. Well, point number 1, you have next Tuesday, the next exam. I got it open from 7 a.m. to 11:59. As before, give yourself plenty of time to complete it. And it's going to cover chapters 4 through 6. I'm available one more time on Mondays if you have any questions to come to my Zoom office time between 1 and 2 on Mondays. And again, if that doesn't work time-wise, feel free to reach out to me and we can make alternative times for you. Okay, so let us go back to the chapter on the Lewis dots. Well, before I begin, are there any questions right now with respect to chapters 4 and 6 that maybe you want to ask about or go over? Okay.
What's
right.
the limit for the exam again?
Pardon me?
What's the time limit for the exam again?
It's open from 7 a.m. to 11:59 that day. So you got all that day to knock it out. Give yourself a good, your average about an hour. The average of the last exam was about an hour for everybody. Your time, it is time, 75 minutes, so keep that in mind.
Okay.
But most everybody took an hour on average to complete it. Okay. All right. Okay. Well, let's go back to the Lewis, the dot structures. Okay. We ended up here, but I want to go back. Okay, when we talk about the, let me make sure I got the right one. Oh, yeah, we're going back too far. Give me a second here. Yeah, of course, I can't find it now. Okay, there we go. Now there's 2 types here of Lewis dot structures. The one that deals with the atoms are pretty straightforward, okay? All you got to remember is how many valence electrons they have. And so looking up the atom, looking at its position, just put the dot that represents an electron to give you the Lewis dot structure for the atoms individually. Okay, so potassium is in group 1. 1 dot represents 1 valence electrons. So those dots represent the number of valence electrons. You go across all the way to iodine, it's in group 7, 7 valence electrons. Therefore, its Lewis dot structure is given as follows. Okay, magnesium going to the left from iodine. Group 2, silicon group 4, oxygen, obviously group 6. So those are for the particular atoms. Now, with respect to the chemical compounds, the Lewis dot structures, the function here is to give you an idea as to what the structure actually looks like. And so if you haven't downloaded the shapes table, do so, because we'll use that. Because using the Lewis dot structures, we're going to define a general formula given by the first column there, A, B, and E, where A represents the central atom, okay, which you'll always be told what the central atom is, and B represents whatever is bonded to the central atom. And then E represents any what we call lone pair of electrons to the central atom alone. Has nothing to do with lone pairs that are attached to B or anything else, just to the central atom. Once we define the general formula, we come to the table and we find that general formula, which then would define for us the geometry of that particular compound, which is given in the next column, to give you a kind of three-dimensional perspective of what it looks like. And then in the third column to the right is a particular name for that geometry, okay? And then finally, the final column gives you what is called the bond angle, and that is the angle between the groups that are attached to the central atom. For example, if you look at the very first one, AB2, there's a bond angle between the B components, or the B atoms, of 180 degrees, okay? And the shape of that is linear, and obviously there's the bond angle. If we look at the next one, AB3, okay, you can see that that bond angle again represents the distance between the B atoms. In this case, it's called Trigonal Planar, and it is 120 degrees. Now, that line, don't forget, that line that is put there in the model represents 2 electrons. Let me get an arrow here. So that line sitting there and that one is the way we represent a bond, okay? A bond between, in this case, A, whatever A may be, and B. And that also represents 2 electrons, because every single bond, because there's one line, has 2 electrons. Now, the reason they have that configuration, remember that there's a total of 6 electrons around the central atom here, and they all have negative charge, okay? And so those 6 want to repel each other and to find the maximum position that they can have and be stable, okay? So 120 degrees for the AB3 is the configuration that gives us the maximum repulsion of the bonds, and that is called trigonal planar. Now we get to the next one, AB4. Again, we got that bond angle is 109.5. That is an angle between 2 Bs, whatever B may be. That configuration is called tetrahedral, and generally is the most common type of configuration or geometry that you find for chemicals. Again, that line represents a bond, and we have 4 bonds here with the electrons, each one having a total of 2 electrons. So we have 8 electrons there that are repel each other. And therefore, that configuration gives us the maximum separation of the charges of the electrons. The next one, we have AB2E. An E, again, represents what we call lone pair. They're not bonded. They're situated on the central atom. Okay? They're not bonded to anything. And in this scenario, we got an AB2, meaning there's two atoms bonded to the central atom, A. Now, because those lone pair are not bonded, they take up a lot of space. They're not being shared with another atom. The result being that this bond angle between the B's is much less and shortened much less than 120 degrees as compared up here to the trigonal planar configuration. Okay. Moving down, the next scenario. Oh, let me clear this. The next scenario is the AB3E. Again, we have three moieties, three atoms bonded to the central atom, but we also have an E. And that E represents, again, lone pairs on the central atom. Because they take up a lot of space, as I mentioned with the AB2E scenario, okay, that bond angle between the B's is much less than 105, which is the standard bond angle between in the tetrahedral configuration. Okay, I got a question. Okay, when I say the lone pair denoted by the two dots, okay, they're no different than what is denoted by the arrow, okay? In this case, the arrow, that is a bonded pair. They are bonded. Two moieties, in this case A and B, are bonded together and they're sharing those two electrons. So those are called bonded pairs. When they are not bonded, they're just sitting on the central atom, those two dots, and that kind of that shape is, it kind of denotes the shape, that little oval shape that you see there. Those are two electrons, and those guys are called lone pair. They're not bonded together. They're just sitting there on the central atom. Does that kind of help you out a little bit, Amanda? Okay.
I was meaning more along the lines of, like, when you're trying to figure out the formula, how do you know right off the bat if it's going to be a lone pair?
Yeah, and we will do an example of that, okay? Because we're going to be counting the valence electrons, and we're going to use the Octet rule to determine if I got a pair left, where can I put it? Okay, and we'll do that. We'll do that example here in a second.
Okay, all right, thank you.
Sure, no problem. All right, and so going on down, the last example is here we have the lone atom A. In this case, we have two lone pairs, and they're going to take up a lot more space compared to one lone pair, and therefore our bond angle in this case is really, we should add like much less than 109.5. We should really have two left arrows, because those lone pairs, we got 4 electrons, 2 there, 2 sitting there, and they take up a lot of space. They repel each other. And so that bond angle between the B's, whatever B's are there, and this is a good example, would be water, H2O, where the B's could be represented by hydrogen, and then A could be represented by oxygen, okay? Now, we use this table to give us the name, the configuration geometry, and the name of the shape, or the name of the geometry, plus the bond angle, okay? Now, how do we go about to figure out the general formula? Well, that brings us to, let me clear my drawings, let me go back to the slide. Okay. And here's the example we utilize, where we use the example to begin with H2O. So what do we do first is we add up all of the valence electrons that each atom brings to the structure. Now, in this case, your oxygen is the central atom. And so, like I said before, you'll always be told who the central atom is. So that means that oxygen's sitting there in the middle, and then everything else that you have in that structure is bonded to the central atom. So the way it's written, those two hydrogens are going to be bonded to the central atom. So we first add up all the valence electrons. We know that hydrogen has one valence electrons, but there's two of them. So we got to count for that. There's two valence electrons. Okay. And then we look up the valence electrons for oxygen. It's in group 6. Therefore, there are 6 valence electrons for oxygen. We tally up the valence electrons. We have a total of 8 valence electrons to work with. Now, what I just generally like to do is you always should end up with an even number, okay? If you do not add up with an even number, then there's a problem someplace with the addition, or maybe you misread the number of valence electrons for that atom. Okay, and Josh, like I said, an even number, but more so a number that is divisible by 2. And so once I figure that out, that I got 8 valence electrons, that also tells me that I have 4 pairs of electrons, because every bond is a pair. So for me, it's easier to keep track of the pairs than count each individual electron. In this case, we only got 8, not too much of a problem, but you can end up with 32 valence electrons. And I just, divide that by 2 to give me 16 pairs, which is a lot easier to follow. Also, too, when I start drawing structures, I can just simply draw a hyphen or a line. That line represents a bond, which is 2 electrons. And if I need a double bond, I hit 2 lines, okay, which I'm represented here by the equal. Okay, that's a double bond. Each line represents 2 electrons. So I got total 4 electrons in the double bond. I don't have a triple bond, but you can see 3 lines, 1, 2, 3, okay, to represent a triple bond. All right, so now we have the number of valence electrons, and we can quickly put the oxygen down and draw the first structure, okay, which would be, hold on, let me do it this way. I can draw it, hydrogen bonded, oops, capital H. Do make sure you use the capital for the atom element. I can quickly draw that structure because I know that oxygen is the central atom. Each line represents a bond. So I took care of 2 pairs. So I have 2 pairs to work with because I have a total of 4 pairs to work with from the beginning. Thing to remember is once you calculate the valence electrons, that is what you work with. You can't arbitrarily just add more valence electrons because you just can't create them, especially if they come from a specific group. That's the number you have to work with, okay? Now, Amanda, to answer your question here is, where do I put those other 2 pairs? Does everybody see here the way I drew H2O that I took care of 2 pairs? Okay, does anyone not see that? Okay, because I got 2 lines there. So that means that I have 2 pair left to work with because I started with 4 pairs, okay? And now I have to think about the octet rule and the duet rule. Duet rule for hydrogen, only 2 electrons around hydrogen. So I cannot put those 2 pairs on the hydrogen, correct? Because hydrogen's already happy with its duet. There is 2 electrons on each hydrogen. already. So the only place I can put those two pair, is on the oxygen. Because right now, if you look at the number of electrons around oxygen, there's only 4. Okay? Those 4 are being shared by the 2 hydrogens, so they count to the hydrogen and they count to the oxygen because they're being shared. I can't put them on the hydrogen because it violates the Duet rule, so the only place left has to be on the oxygen. Well, let me see if I can draw that. And so I can very quickly draw a line right there and draw a line right there. Okay? Now, around the oxygen, I have 4 lines that represent a single bond or 2 electrons. So if I count the oxygens around the electrons around oxygens, I have a total of 8 electrons, okay, which is consistent with the octet rule. Okay, and I count the electrons around the hydrogen, I have 2, which is consistent for hydrogen's Duet rule. And then I go back and I count all the electrons I have. There I have a total of 4 pair, which is consistent with what we calculated in the beginning. And Ali, you asked the question, if it's a double bond, does it have 4 electrons? That is correct. A double bond, like I wrote the equal sign, okay? Normally I can draw this on the board if we were on, doing face-to-face, but that equal sign represents 2 lines or a double bond, and each line is 2 electrons. Therefore, I have a total of 4 in the double bond. 3 lines represent a triple bond. Each line has 2 electrons, so there's a total of 6, okay? And when you go back to count the electrons, in this case here, with respect to water, what we have here, after everything's done, we have 2 bonded pair of electrons, okay? Because those 2 are bonded to the hydrogens. And we have 2 lone pair, okay? 2 lone pair, because those 2 on the oxygen are not bonded to anything. They're just sitting on the oxygen, okay? And so now, once we figure out the structure and where all the electrons are and all the pairs have been accounted for based on the valence electrons, we create a general formula using the ABE notation. And so there's always an A, without a doubt, that's the central atom, okay? And we have B because there there's 2 atoms attached to the central atom, and there's 2 of them, so that represents a subscript 2, okay? Because I don't have the subscript function here. And E represents the lone pair. We just stated we have 2 lone pair, so we have an E, okay? Subscript 2. So that is the general formula for H2O. Once we know that, we go to the shapes table and look for AB2E2. And there it is, the last entry, okay? The very last entry. The general formula is AB2E2. The geometry is given. That is the kind of 3-dimensional structure of water in this case. And that bond angle is much less than 109.5 because of those 2 lone pair on the central atom, in this case, oxygen. And the name for this geometry is called bent. Okay, so I think, Amanda, you had that question. Does that answer the question about the lone pair? So once you filled out all of the octets for all the atoms you're dealing with, what you got left, you have to figure out, where can I put it? And 9 times out of 10, the last place that you can work with it would be in the central atom. We'll do a specific example here in a minute.
Yeah, it kind of answers my question. It was one of your other examples that you were kind of talking about in the last class that we had to end on.
Okay.
It was like with the example HCN.
Yes.
And yeah, so like
Okay.
the formula I thought I came up with
Mhm.
for that one was AB2E.
Okay.
I don't know if that's right.
Okay. Because I see you looked at the structure and you saw the lone pair of nitrogen. I'm assuming right now, right?
Yeah.
And you probably thought, okay, that's a lone pair. However, look at the first entry up there. It says carbon is the central atom.
Yeah. Okay. So in
Okay.
that case, it would just be AB2.
AB2, exactly. Okay. So you all, when you think there's a lone pair, you know, it depends on who the central atom is. In this case, it was defined and it said carbon's the central atom, which in this scenario has no lone pair. If we would have said nitrogen was the central atom, then that would be correct. Okay. But structurally, it wouldn't be possible with this particular formula for nitrogen to be the central atom. Okay. Let me do another one.
So what
Let me
you're
pull
saying
up.
is that lone pairs only come into play if the central atom isn't completely filled, like to fill its octet.
Yes. Well, let me do an example of ammonia.
Okay.
Okay. And you'll see how the lone pair that we have to put it someplace. And the only place you can put it will be the central atom.
Okay, I got it. Thank you.
Okay. All right. Let me pull up, where'd it go? Where'd it go? Let me pull up a Word document here because this allows me to do subscript. All right, let's do ammonia. Oh, wrong one. Ammonia has that general formula. NH3. This is the nasty smelling window cleaner, ammonia cleanser. That is the structure. It is nitrogen with 3 hydrogens, okay? Now we have to come up with a general structure. Now, the central atom, which either be highlighted or underscored, will be given to you, okay? Not highlighted, but it'd be bold. In this case, I underscored it to designate that is the central atom. Okay, so what is the first thing we do? We count up the valence electrons, correct? So nitrogen, how many valence electrons does nitrogen have? Well, we go up to the periodic table and we see it's in group 5. So there's 5 valence electrons, okay? Hydrogen is in group 1. It brings 1 valence electrons, but there are 3 of them. Correct? Would everybody agree on that? So we have a total of 3 valence electrons for the hydrogen. Again, we had the scenario where the total valence electrons equals 8 or 4 pair. So far, so good? All right. So we can very quickly, because the nitrogen is a central atom, we can put in, and let me see if I can do this with nitrogen. And let me draw that. Okay, do you see what I did? It's not square, but I try to attempt to draw the structure. The first structure I come up with is that I bonded the 3 hydrogens around the nitrogens. Okay. Now, how many pairs does that take care of?
6.
Okay, not how many pairs?
3.
3.
Pardon me? 3, exactly. 3 pair or 6, you're correct, 6 electrons. So I have 1 pair left to deal with, or 2 electrons to work with. Now, I cannot put it on hydrogen, okay, because that will violate hydrogen's duet rule, because hydrogen's already sharing 2 electrons of nitrogen, each one of them. So where is the next logical place to put this?
On nitrogen.
On nitrogen. Okay, so I draw a line like that, or I can do 2 dots, or draw a line or 2 dots. And so now I go back and check, okay, do I still have 4 pairs or a total of 8 electrons? Yes. Okay, I got 4 lines there. So I still maintain my 8. I can't add, I can't subtract. All right, so now I draw my general structure. And what would be my general structure here? Who would like to take that?
Are you talking about the formula?
Yeah, well, the general formula, yes, excuse me.
It would be AB3E, right?
Is it
You
Ben?
got it. It would be AB3 E, okay? That would be my general formula. So now with my general formula, I go back to my shades table, okay? And I look for AB3E, and it's the second entry. Okay, you can see where that lone pair exists on the central atom. I got the 3 B's, which in this case are hydrogen. And so its name will be trigonal pyramid. And its bond angle between the B's is much less than 109.5. Okay, now let's do another example where we get a lot of electrons. Let me go back up to share and we'll start from the beginning. Let me think of one. Okay. This is a chlorohydrocarbon. This is carbon with 4 chlorides bonded around it. And the central atom is carbon. Okay. So let's start with the valence electrons. So carbon brings in how many? Carbon's in group 4, correct? So we got 4 valence electrons. Each chloride, what chloride is in group 7, okay? So each one brings in 7 valence electrons, but there are 4 of them. Okay? And so now what do we have? We got 28 valence electrons that are coming from the chloride. And so our total would be the 4 from the carbon and the 28 from all of the chlorides to give us 32 valence electrons to work with, or 16 pair. Okay. Everybody with me so far? Now, the formula, and it's going to be a little tough to draw it, but let me see what I can do. We have carbon as the central atom, and so I can very quickly put carbon in the central atom, go ahead and bond through those chlorides, and let me see if I can do another space here. It's gonna be tough here, but let's see if I can do it. Let me back it up a little bit. Got one there. Okay. Let me draw a circle. Now, when I draw it on paper, I can very quickly, not disregard the fact that they're so long, but because the tool that I have is limited, but we can, just the line represents a bond. All right, so does everyone agree that we are taking care of 4 pairs?
Yeah.
Okay, and so with 4 pair taken care of, how many pairs do we have left over to work with?
12.
We got 12 pair exactly. Now, can we put any more on the carbon?
No.
No, because the carbon is full. The carbon has its octet fulfilled. So the only other place that they must go has to be around the chlorides. And so I can very quickly go, there's 1, there's 2, there's 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay? Now, go back and double check to make sure you have 16 pair, or if you want to count them individually, 32. And do we still have 16 pairs sitting up there? We do. Okay? And so in this case, how many do we have? 12 pair of electrons on the B atoms. They're not on the central atom. So yes, they're lone pair, but they will not count toward the E because they're not on the central atom. So what will be our general formula here?
AB4.
Exactly, AB4. And so therefore, once we go back to the shape table, we look for AB4, and lo and behold, there it is. AB4, its geometry is given. That is fairly the most common geometry that there is out in nature. It is called tetrahedral, and its bond angle is 109.5. Okay, 109.5. I think I lost my drawings and my bonds, but another. Now, one thing we just did was ammonia, NH4, NH3, excuse me. But if you look at ammonia or nitrogen, underneath of nitrogen is phosphorus. And if you do the same thing, if you went to pH3, you're going to come up with the same structure because you have the same number of valence electrons you're working with. Nitrogen and phosphorus are in the same group. So they're going to bring in the same number of valence electrons. Hydrogen always brings the same number of electrons. Okay, so you would get the same structure if you had nitrogen or phosphorus bonded to hydrogens. Let me give you one that's a little more complicated. Okay, let's erase this. But it's a lot more challenging. That would be, oops, I lost my, boot it up a little bit. Sulfur dioxide. Okay. Now, when I gave you the structure for carbon dioxide, which is right there. Carbon dioxide, you end up with this structure. You end up with the valence electrons that you have. You end up making double bonds between the carbon and the hydrogen. Okay? And here we have the example of sulfur dioxide. You might think, well, maybe it's the same structure, but because we have one central atom and two moieties bonded around it. But you can't go by that. You have to go by where that atom is on the periodic table with respect to the group. So in this case, sulfur is our central atom. Okay. And so we do what we normally do. Sulfur brings up how many, sulfur has how many valence electrons?
6.
6, exactly. And oxygen, oh, let's put a comma there. Oxygen brings in how many?
6.
Yeah.
That'll bring in 12. No, 6.
That, it would be 6 times 2,
12.
right? So that brings in 12. And so for a total valence electrons, we have with 6, 18, right? 18 VEs, valence electrons, or how many pair?
9.
9 pair, okay? All right, so sulfur is the central atom. Oxygen, the two oxygens are bonded around the central atom. So we can very quickly draw this structure. Okay? Because oxygen is bonded around the central atom. The two oxygens are bonded to the central atom. So that took care of how many pair?
2.
2 pairs. So we have not almost a 9 pair. We have 7 pair. I got to work on my math. 7 pair to work with, right? We got to put them someplace. So you can. I like to start from the outside atoms and work my way in. So doing what I did earlier, I'm just going to start in the oxygens, and I'm going to start drawing. There's 1 pair. 2 pair, 3 pair, 4 pair, 5 pair, 6 pair. Okay, so 6, 7, 8. I got 8 pair there. Now, I cannot put them on the oxygens anymore. Right? I got 1 pair to place somewhere. Where must they go?
On the sulfur?
Exactly. Because I can't put them on the oxygens anymore. Why? Because the oxygen, there's 8 electrons around the oxygens already. Okay? And now count all my bonds there. How many pair do I have? Do I still have 9 pair? And that's the important part. You got, as you make these drawings, go back and check to make sure you didn't lose a pair someplace or mistakenly added a pair, which you don't want to do. So if you count the lines there, you will see that I have 9 pair or 18 valence electrons, okay? Now I check the octet. The oxygens on both sides are happy because they got 8 electrons around it. But the sulfur, how many electrons are around the sulfur?
6.
That's correct. 6 electrons around the sulfur. And so remember when we talked about making double bonds or triple bonds until such point you're at the point that everybody is happy with respect to the octet. And so in this case, you can take a pair from the oxygen, okay, and make a double bond. And so I could, let me, I can make a double bond. And so let me draw this, that, got the sulfur, make it equal, and then the oxygen, okay? And then I go back and I put the oxygens, they're paired up. I gotta work on my drawing skills here. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. I still have 9 pair, correct? By making a double bond, in other words, taking a pair from either of those oxygens that you want and make a double bond. Now check to see that the octet is fulfilled with everybody. The oxygen in the right side with the double bond has 8. Sulfur in the middle has 8. And the oxygen on the left has 8. I still have 9 pair, okay? So I'm good to go. Everybody has the octet fulfilled. Now I write my general formula. Okay, what would be my general formula here? Well, obviously A and obviously B, okay? What else do I need?
2E.
Exactly. So 2, subscript 2, because I got 2 B's around the central atom of A. And then on the central atom, I have a lone pair. Okay.
I have a quick question. What would this look like as the Lewis dot structure?
As a, well, just take those lines off. That is the Lewis dot structure right there. But take those lines off and put 2 dots. It was to be
Okay,
kind of different.
so there's only going to be a double bond between one of the oxygen?
Yes,
not both?
that's right. And whichever one you put it on, you can put it on the left side or on the right side, you'll be correct. Once you get into chemistry 151, 152, you're going to get it. Those two the double bond can exist on both sides, and we create a special structure for that. But for us right now, you make that double bond either on the right or the left, and that is correct. And that is the Lewis dot structure for carbon dioxide, not carbon, sulfur dioxide, okay? Nasty smelling gas. And if you wanted the dots, just take, everywhere you see a line, you can just put 2 dots. If you're more comfortable with the 2 dots representing electrons, that's fine too, okay? And so here we got E. So that is a general formula because we identified that on the central atom, there is a lone pair denoted by that arrow, okay? And there are 2 atoms bonded around the central atom. And so now we go to the shapes table and look for AB2E, which is there, okay? AB2E, there's a geometry for that lone pair, and it's bent. And that bond angle is less than 120. Now, why is it important to know this? Because once we figure out the structure or the Lewis dot structure from this gives us an idea about the polarity of the overall molecule. We talked about the electronegativity of the elements, okay? And we're gonna, when we talked about bonding covalent bonds, where there is an equal sharing at this point, I said at this point, we just treat it as an equal sharing. But in reality, there's not an equal sharing when there's a bond. That double bond between the carbon and the oxygen is not equally shared, simply because of the electronegativity, the En. And we find that when there's unequal sharing, that causes one electron or one atom to pull the electrons onto itself, because after all, that is what electronegativity is the ability to pull electrons onto itself in a bonded pair, unlike ionization energy, totally different. And so this moiety here, if you look at the periodic table, okay, and compare sulfur and oxygen, can you make a prediction right now based on what we talked about electronegativity? Which is more electronegative, the sulfur or the oxygen, based on their position on the periodic table?
Wouldn't it be oxygen?
Exactly. Now, how would you determine that? Well, we go to the periodic table. Look for oxygen.
It's slightly closer to fluorine than sulfur.
Exactly. Remember, our reference point was fluorine. So the closer you get to fluorine, the higher the electronegativity. Sulfur is in period 3, further away from fluorine. Oxygen is much closer, it's right next to fluorine. So oxygen is a lot more electronegative. What does that mean? That means for that particular bond, the electrons, and let me draw it with a special arrow. The electrons are drawn from the sulfur to the oxygen, okay? And the same is true in the other direction of the bond. The electrons are being pulled toward the oxygen simply because the oxygens are more electronegative. The result is that this particular structure is what we call polar. We have polar and nonpolar. Those are their properties. Oil-like, which is nonpolar, and water-like, which is polar. And so we can make a prediction because the overall polarity of this molecule is polar due to the bonds, that the solubility of sulfur dioxide will be much greater than the solubility of compared to carbon dioxide. Why is that? Well, let me show you why. We're a little bit early on this introduction, but I think this is a good spot. We already looked at sulfur trioxide and realized it's bent, okay? And so if we do the same exercise for oxygen, which you saw the structure there earlier, we get a double bond, 2 double bonds, okay? Now, the question would be, is carbon dioxide polar? Well, what we do first is we look at the bond and determine whether that bond between carbon and oxygen is polar. The fact that they're 2 dissimilar atoms automatically says yes. Carbon and oxygen are dissimilar. There's a change in polarity. So the next question is, okay, who's more polar? Well, we go to the periodic table and we look for carbon and oxygen. And who's closer to fluorine, carbon or oxygen?
Oxygen.
Oxygen. That means, again, here in this scenario, that oxygen is a lot more polar. Therefore, the electrons that are shared are pulled toward the oxygen. And let me draw that arrow. And so we have a pull of electrons from the carbon to the oxygen. And we have a pull on both sides. Okay? Now, the pull is in opposite directions. Okay? And what happens, because they're in complete opposite directions, that means the electronegativity and the pull of electrons, that those 2 arrows cancel each other out. The result is that carbon dioxide is nonpolar. Now, when we looked at sulfur dioxide, we had the pull going in this direction. And because of the structure that it had, the other direction was more of an angle because of the ABE moiety, ABE2 general formula. And so in those two arrows do not cancel each other out. So the polarity for SO2 is yes, overall polarity, yes, that's a polar species. carbon dioxide is not very polar because the polarity in the bonds cancel each other out. So now I can predict which would be more soluble in water. I can predict that carbon dioxide is a lot more, sulfur dioxide is a lot more soluble in water due to the polarity nature of the structure compared to carbon dioxide. And it is. If you take a soda pop and you shake it, what happens? Take a soda pop, when you keep the cap on, what happens to it?
It bursts.
Yeah, it bursts, it gets pressure builds up because carbon dioxide, even though it's in solution, is not very soluble. If it was soluble, it would not escape very readily and pressure wouldn't build up. It's because the solubility of carbon dioxide is in water is not really that high. A question was, does the rule go for any element? Yes, the question about electronegativity, that is a true statement. That fluorine is your benchmark, and any as you go toward fluorine, the electronegativity goes up. Okay. All right. So we kind of introduced this a little bit early, but that's okay. As far as polarity, so when we do a compare and contrast, got a question. The question is, as far, when it comes to, don't confuse the two between being polar and electronegativity. Remember, electronegativity is a measure of the affinity for electrons being pulled onto itself. If make sure I put this correctly so not to confuse the things. Electronegativity in a bond determines which direction the sharing of those electrons occur to form what's called a polar bond. If those polar bonds are canceled, just like the carbon dioxide example where the arrows are going in opposite direction, then the polarity of the bonds, of the two bonds, cancel each other out, resulting in a nonpolar moiety. If they do not cancel out, like the case of sulfur dioxide, due to the structure, which we determine using the Lewis dot structure, that it was the AB2E moiety, which gives us the bent structure. And that means that the polarity of the bonds do not cancel out. Therefore, it is a polar species, okay? In general, as a rule of thumb, if you have a compound that has polar bonds, the net result is for that compound to be polar, unless the polar bonds cancel each other out. The previous example we did was carbon tetrachloride. We did the CCl4, and we came up with the tetrahedral. Well, between carbon and chloride, there's two different atoms, so automatically it's polar, okay? It's a polar bond. And if we compare the polarity of the two, the chloride is, right next to fluoride, even though it's one group down, but chloride is a lot more electronegative than carbon, okay? Because carbon is much further away to the left. So in that moiety, the CCl4, we have 4 polar bonds. We would anticipate it to be a polar compound, but it's not, because those 4 polar bonds in the tetrahedral position mathematically cancel each other out, resulting in a non-polar compound for carbon tetrachloride, CCl4, the one we just did. Okay. We'll have some more of those examples as we proceed, so hopefully if you're a little bit taken aback here, kind of introduced it a little bit early, but we'll do some more examples and hopefully clarify. Does that answer your question, Ali?
Yes, thank you.
Okay. All right, so where were we? All right. Now, one thing to note with respect to polarity, anytime you have a lone pair in the central atom, you always will have a polar compound, no matter what. Again, why? Because even though you may have a polar bond, okay, and you might think, okay, I got polar bonds, I'm gonna have a polar moiety. The fact that you got a lone pair, and because they take up a lot more space, and that angle now is less than 109.5, the polar bonds in this example for ammonia do not cancel each other out. So you end up with a polar species. Anytime you see a polar lone pairs, you have a polar compound, regardless of what's bonded to it. Same would be true for water, H2O. We did that example. Water has two lone pairs, extremely polar compound. The most polar thing we have. I think there's one more compound a little bit more polar than water, but water is the most polar thing that's out there. Okay, so anytime you get a lone pair and you come up with it, you have a polar bond. With that in mind, there's only, when I said when I have two different atoms automatically think polar bonds, there's only one exception, and that is a bond between carbon and hydrogen. The electronegativity between the two are essentially the same, okay? So therefore, there's an equal sharing of electrons in a carbon-hydrogen bond, and therefore it is nonpolar, okay? What about the carbon-nitrogen bond here? Would you consider that polar or nonpolar? This bond right here.
That would be polar.
Very polar, exactly. And in this scenario, this would be a very polar compound because on the left side, we have a nonpolar species, and the right side, we have a polar species. This polarity is very important with everyday life. Shampoo works that way, and detergent works that way because molecules of shampoo and detergent and soap are very big. And what they do is on one side, they have a very non-polar part of it, and the other side, they have a very polar part. The non-polar part is what dissolves and gets rid of the oils and greases because they're very non-polar. And then they get washed away for the polar part where the water comes into play. So polarity has a very big factor, which is related to the electronegativity of the atoms in the bond. Okay. Now, would you say that hydrogen gas is a polar species? Thank you. Would you say that hydrogen, bromine, chlorine, fluorine, oxygen, what would you predict as far as the polarity of those guys? Hydrogen gas, chlorine, bromine, iodine. Does that ring a bell with those guys? What are they?
They're nonmetals.
Well, they're non-metals, but what else?
So wouldn't that mean that their polarity would be high? Because
well, not quite. I like what you're thinking, but let me step back a second. Hydrogen, fluorine, bromine. Remember, have no fear of ice cold beverage.
Oh yeah, they're diatomic.
They're diatomic. Okay, and so we have the example I gave here. Okay, I have a bond between the two bromines, just like I would have a bond between two hydrogens, okay, and chlorine and all the diatomic ones. Now, I have two bromines bonded to each other. What could you say about the polarity of that bond? Would you predict it to be polar or nonpolar?
It would be nonpolar because it would cancel each other out, right?
Well, not cancel each other out, but I got bromine with the same electronegativity as another bromine. So there's an equal sharing of that bond between the two bromines or between the two hydrogens or between the two chlorines, all the diatomics. There's an equal sharing because the electronegativity of those atoms are the same, okay? Therefore, you don't have a polar bond. So all of the diatomic molecules, all 7 of them, all those bonds are nonpolar, plus the carbon-hydrogen bond. So you only have 8 examples of a nonpolar bond, which results in a nonpolar compound, okay? Therefore, mixing those nonpolar species in water wouldn't go very well. The polarity of water is way too high. It's like almost mixing oil and water. But mixing them in an oil-based solvent will be fine because they're nonpolar. Remember, light dissolves light, okay? Light dissolves light. Things that are oil-like or nonpolar will dissolve in oil-like solvents or nonpolar solvents. Things that are polar will dissolve in polar solvents. Y'all know Italian dressing, does it mix? Any Italian dressing eaters out there? Don't you have 2 layers? You got your Italian, you got your oil layer and you got your water, your aqueous layer. They don't mix because again, oil is very nonpolar. And water is obviously.
Is that kind of like the same thing with like natural peanut butters?
Separate?
Separate?
Well, natural, well, okay, that would be like, when they say natural, I'm not quite sure. They're saying they actually, they're probably thinking that they grew them where the soil is not full of all kinds of other chemicals. But the actual.
Well, I mean, like, I don't know of anyone like who all has ever like purchased like a natural peanut butter from the store, but like when you purchase it, it's in 2 separate layers, and they require you to kind of mix it up to get the consistency back to where it should be, but it naturally just separates.
Yeah, I think the difference is in how they're prepared, because the structure of the peanut butter is the same. The overall structure is the same. It just some of the foods that they're have added preservatives and they put emulsifiers, all kinds of other things to keep it intact. A lot of your detergents you use for your automatic detergents. This one I know for a fact because I've done some research now back in undergraduate. Your thick detergent cleansers that you put in your automatic, you put in there emulsifiers and all kinds of wetting agents to keep everything together. So the natural peanut butters, my guess would be that they don't have all these other emulsifiers to keep the oil and everything together, and therefore they separate en route to the store and when you purchase it. Hopefully that answers it. But the structure itself, and when I hear the term organic, being an organic chemist, I kind of cringe because the structure of a fatty acid, whether I get it from a different source, is the same. It's just where it came from. I think another term should be used. They're both organic. All right, so let me think. I'm going to erase all this. Any other questions? Hopefully that helps out. We did the carbon example. Now, which one more question? Let me answer that. Oh, 5-minute warning. Okay, well, that being the case, I got the 5-minute warning. Maybe I better not get into this one because here, basically, go ahead and jump ahead if you want, but we're going to take polyatomic ions. Now, what are these polyatomic ions? Well, Guess what? I'm pointing back to the periodic table. I told you in the beginning, I always use the periodic table. In fact, I got another one prepared for you for some of the topics we're going to cover. But on the periodic table, far left corner, we have what are called polyatomic ions. And we're going to be using these quite a bit. These are ions that are covalently bonded together. Notice that NH4 plus in the bottom left corner, top left of the box. And, you know, those are covalent bonded, but overall, because of the structure, they have a charge. And they're ions, and some of them are soluble in water, some of that, but they have a charge. So we're going to write the Lewis dot structure for some of these polyatomic ions. The procedures are the same, okay? Notice that the polyatomic ions, let me scan it up a little bit, that some of them, we only have one positive charge. That's the ammonium ion, NH4 plus. The other ones are anions, they're all negative charge. You probably eat these every day and don't know it. There's a lot of sulfates out there that we eat. If you drink wine, for example, one reason I don't drink wine is because the sulfite messes with my arteries and it gives me a headache. So sulfites tend to be I think they call them vasoconstrictors, I believe. So sulfites are found in a lot of foods. This one here, you make chocolate chip cookies, you probably use this. Good old-fashioned baking soda, okay, bicarb and carbonate. If you use Drano or liquid plumber to unclog your bathroom or your sink, you would definitely use some of this, hydroxides. Some of you ladies out there with your makeup and your cleansers and stuff may even have a hydroxide cleanser. They tend to dissolve the tissue and kind of give you a new layer. So be careful of that. You don't want to dissolve too much, because if you ever got any liquid plumber on your finger, it might be a little slimy. You might think it's the chemical, but it's not the chemical. It is the hydroxide that is denaturing your tissue. So wash your hands immediately. Sodium acetate, I'm sure there's a lot of that in additives found in food and phosphate. Anyway, we're going to be talking about how to write Lewis dot structures with these polyatomic ions. So, let me see. Let me stop it here. I'm going to ruin your lunch because I'm going to show you all the chemicals you eat. All right. I will continue next Tuesday with this particular chapter. And don't forget, Monday I'm there. If you need some assistance for the exam, give yourself plenty of time. Don't wait till 11:58 p.m. Okay?